Okay, so let's get started. Welcome back, everyone. So before we begin, like few usual announcements. One about assignment 2 regrading. So one of the TAs responsible went for vacation, so we couldn't do some of your regrade requests on time. Okay, but those that involves other TAs, like they were graded as quick as possible, as I promised. But there is one particular sub question set which is not yet graded. So to give you more time for interaction, so we will extend the deadline for regrade requests. So probably until end of Friday. The TA is back on Wednesday morning, so we're going to give him time until end of Friday. So just for this one time, okay? So, but next time, we will make sure that everybody's available during the regrade period. There's always something to fix. Okay, and I hope your A3 is going well. So there's a question about A3 in the chat. So as for hyperparameter tuning, if you want to use grid search, we should use cross-validation. However, here we have a validation set separately. Is it possible to combine validation and training set and then use cross-validation? Now, if any of the questions ask you to report validation set accuracy, then probably you cannot do this merge. Is there a question which asks for validation accuracy?
Yeah, so they can't merge it.
Okay, so then you cannot merge it. So if you want to do cross validation, you should do it with the training set. So, but you don't need to do cross validation for grid search. Why do you need to do cross validation for grid search? If you want to do grid search, just consider all possible hyperparameter configurations. Oh, okay. So it seems in Piazza, it is mentioned that we could merge it. And okay, so we will. Okay, then I don't want to say a different answer. So I will check Piazza and figure this out after this lecture. Okay. And other than that, one last thing is about Kaggle. So tonight is a deadline for you to form the team, but after the lecture, we're going to release the data and problem statement. Okay. But remember, you should form your team, merge the team members, you sign up and then you merge the team members and then make a submission. If you make a submission without merging, you'll be penalized. Okay, so don't make any submissions, even a sample submission, before you merge to the teams. And don't forget to sign up in the spreadsheet as well, because in the end, we will be linking your team names to the spreadsheet to distribute your marks. Okay, so I want to highlight a couple of things, even though the instructions are not yet out, because these are common mistakes that people do every year. So we will release a detailed problem statement. Okay, but one of the most important constraints of the competition is you should only work with the data provided to you. You cannot add other data sets while training your method, and you cannot use any pre-trained models. Okay, so the challenge is to do the best that you can with the given data. So you cannot use pre-training. If you use pre-training, your team will be disqualified. Similarly, if we get to know that you have used an external data set to improve your performance, again, you'll be disqualified. So just work with the data that is given to you and try to improve the score as much as possible. Okay, so any questions? Okay, so there were questions about the final exam in Piazza. I'm not sure if it was answered. So the final exam will happen on the date and time given by the university. So I don't know what the time is. Arjun, do you know the time for the final exam? Okay, so anybody knows what's the time for the final exam?
18th.
Sorry?
18th of December.
Okay, and what time?
Oh, 1:30.
Okay, so it's 18th of December, 1:30 p.m. Okay, so it's going to be 3 hours from 1:30 p.m. Okay, so some of you emailed me saying you want to travel and like what exactly is the time and so on. Like some of you emailed me about the time zone difference because there is still some students who are taking the course completely remotely because of visa issues. However, the time is fixed. So even if the time zone doesn't work for you, like you should make time for the exam. Like, so if you are traveling, make sure that you are not traveling on that day. Okay, so you could travel before or after. We cannot accept any excuses in submission saying, okay, I was catching my flight, so I couldn't submit my answers, like, and I submitted 4 hours late. No. So whatever the given time for the exam, like make sure that you are available with good internet connection. So you'll start the exam, finish the exam, upload it within the given time. Okay, so given the fact that it is something that you're doing remotely, it is an open book exam.
Would it be possible to have practice exams or like sample questions?
Yes. Okay, so I will, well, have you ever seen the self-assessment questions?
Pardon?
Have you seen the self-assessment questions in the website?
Oh, yeah.
Okay, so my general advice is like if you're very comfortable with all the self-assessment questions, then it is going to be easier for you to do the exam. But self-assessment questions are mostly level 1 questions. It is not very, it doesn't involve a lot of thinking. It's just to make sure that you understand the concept, but we will also test if you can apply the concept in the exam. So it's going to be, exam questions are going to be on an average harder than the self-assessment questions. Probably, okay, given the fact that last year was also open book, and probably some of you have access to the question from your seniors or friends. So I'm going to release the last year's exam as a sample exam, okay? So it will give you an idea of what kind of questions you can expect. Is that clear? Yeah.
You said it's a take-home exam?
Yes.
So the time for the exam is 3 hours on the day of the exam?
Yes.
Oh, okay.
Yes. But if I do a 24-hour take home, then it is going to clash with some of your other courses. I don't want to do that. Also, like it's just easier for you if you do a 3-hour take home instead of 24-hour take home. So, okay. So I think that's mostly the announcements. Let's get started. So last week, like after discussing about decision trees, like we started talking about ensemble methods, right? So specifically, we looked at 2 types of ensemble methods. Like, so can somebody tell me what are they? Okay, there are answers in chat, but I also expect answers from the classroom.
Random forest.
Okay, random forest was an instantiation, right? Like, so what was the general idea? Yeah. Yeah, so bagging and stacking, right? So we looked at the idea of bagging, where you combine many models by taking an average or majority voting, right? Like, so random forest is an example, or extremely randomized trees, or you could just take 10 different logistic regression models and bag, or you could take any model and you can bag, right? So that is bagging. Then we also looked at stacking, which is the idea of learning a meta model, like which will take predictions of a bunch of models and learn to make a prediction by using this combined expertise, right? So we discussed strategy for training such a meta model, like by using the idea of cross-validation, right? So these are the 2 different methods that we have seen in the previous lecture. So today we are going to see yet another ensemble method, okay? So which is the idea of boosting. Okay, now it's going to be different from bagging and stacking. So in the case of bagging, you train all your classifiers, or you can train all your classifiers in parallel, right? So if you want to train 10 different classifiers, you can train them in parallel and then just combine the output by majority voting. So this is all parallel, right? In the case of stacking, it was a 2-level training, right? Like, or 2-stage training, like where you first train a bunch of classifiers in parallel, and then you train the meta classifier on the top of these classifiers, right? Now, boosting is going to be a different philosophy. Like, so in the case of boosting, we're going to do sequential training of classifiers. Okay, let's say we want to train 10 classifiers and combine them. Okay, so bagging is going to train all the 10 classifiers together and then combine them, right? Like, on the other hand, with boosting, we're going to train our first classifier, then we are going to train our second classifier on the mistakes of the first classifier. Okay, so that when you combine these two, they are more powerful. Then you're going to train your third classifier to avoid the mistakes of the first two classifiers. Okay, so as you can imagine, the sequential training is going to make your classifier more and more powerful. Like, so because you're learning on the mistakes of the previous classifiers, right? Like, so you learn to avoid those mistakes. Like, so on an average, like, you're going to get better performance. Is that clear? That's the general idea of boosting. So this specific version of boosting algorithm that we're going to see today is by Rune and Schaffer. Okay, 1996. So the main advantage of boosting is, unlike bagging, which requires a set of good experts, okay, so boosting can actually work with very simple classifiers. Okay, so even if the performance of the classifier is not so great, you can improve it significantly by doing boosting. Okay, or in other words, boosting often works with or can work with weak classifiers. Okay, for bagging to work well, you need really good classifier. Like, so your classifier should already be having like 90% accuracy, let's say. On the other hand, with boosting, even if your classifier is just better than random classifier, okay, like, it's not a very great classifier, it's a very simple, like, just better than random classifier, even then if you boost such a classifier like for many times, you're going to get much better performance. Is that clear? Any questions about the idea? Any question in the chat? Okay, no. Okay, now we need to discuss how exactly are we going to implement this idea, right? So now this is how it's going to work. So when we start our training, we are going to give some weights to all the examples. Okay, initially we will begin with equal weight to all the examples. Let's say you have n examples, then you're going to give 1 by n weight to all the examples. Okay, now you're going to train the first classifier on the weighted loss instead of the normal loss. Okay, where the weight for the loss is given by whatever weight that example holds. Is that clear? So the first classifier training is as usual as any other machine learning method. So except for the fact that I'm going to add a weight. So let's say I have some weight, wn1. Okay, now I'm going to use this weight to learn my first classifier. Let's just call it y1 of x. Is that clear? Now, depending on the mistakes of the first classifier, I'm going to adjust my weights. So I'm going to get wn2. Okay, now this wn2 is going to be dependent on first classifier's errors. Like, for example, let's say there is one training example where the first classifier has good performance, like it correctly classifies. Okay, then you will not do anything to that weight. Okay, however, if the first classifier has made some error in an example, then you're going to increase the weight of that example. So on an average, what happens is errors of the first classifier, like wherever the first classifier made error, like you're going to increase the weight relatively. Is that clear? Now you have this new weight, wn2. Now using this new weight, you're going to learn the second classifier. Okay. Now depending on the mistakes of the second classifier, like you're just going to continuously train, and let's say finally, like if you want to train m classifiers, then finally you have the mth weight, and from the nth weight you get ym of x. that clear? So now we have trained m different classifiers, but sequentially, each focusing on the mistake of the previous classifier. Now, how do I combine these classifiers? Right. So once we finish this training, we are going to take a weighted average of all these classifiers, where the weight is dependent on how good that classifier is. Okay. A classifier which is really good will have more weight. A classifier which is probably like not that good is going to have less weight. Okay. So we are going to combine all these things. Okay. And the combination is based on some weight, let's say alpha 1 to alpha m. And finally, I have this capital Ym of x, which is the ensemble classifier. This is given by sine of summation over m is equal to 1 to capital M alpha m Ym of x. Okay, it's kind of like weighted majority voting, because if this sum is greater than 0, then we're going to call that as class +1, let's say. And if the sum is less than 0, I'm going to call that as class -1. Is that clear? Any question about the idea? Yeah.
Could you please explain a little better about how can a model learn from the mistakes of the previous one?
Okay, we are going to go to that in detail. So I'm just iteratively refining the concept. Okay, so for now, like, it's the higher level idea clear. So the higher level idea is like you train the first classifier, then based on the mistakes of the first classifier, you set some weight. I haven't told you exactly how to set these weights. Then once you have this new set of weights, you train the second classifier and so on. Now, once you finish this whole process, then you combine the classifier weights. Okay. Now there are a lot of missing points here. Like, so what are they? So how do I construct W's, right? And similarly, like, what is this alpha? So I told you that it denotes how good is the classifier, but how do I construct this alpha? Also, how do I learn the parameters of these classifiers, y1x, y2x to ymx, right? So now there are a lot of things that we need to learn. Okay, so let us look at that in a more concrete way. So we're going to consider for today's discussion a two-class classification problem. Okay, so well, there's a question. Does this work for K classes? Of course, you can extend it to K classes. Okay, so we're going to consider a two-class classification problem where there are n data points. Okay, so x n t of n is equal to 1 to cap. Okay, we are going to consider the classes to be +1 or -1. Tn belongs to -1, 1. So clear? So initially, we are going to assign a weight of 1 over n. For all examples. Okay. Okay. So now we are going to see a specific instantiation of this algorithm called Adaboost. Okay, Adaboost stands for adaptive boosting. Okay, so first let us see the algorithm, and then we will talk about like how to design this algorithm from first principles. Okay, so first what we are going to do is we are going to initialize the data weighting coefficient Wn by setting Wn of 1, like for the first classifier, is equal to 1 over n. Okay, now our goal is to train m classifiers. Okay, so we're going to have a loop. So for m is equal to 1 to m, okay, first step is to fit a classifier ym of x to the training data, okay, by minimizing the weighted error function. Okay, my error function is given by Jm, which is nothing but summation over n is equal to 1 to capital N, Wn of m multiplied by the loss. So the loss here is an indicator function, which is y of xn is not equal to 3. Is that clear? So I have a weight for each mistake. So this indicator function basically is 1 whenever the output of the model doesn't match the true label, and it is 0 otherwise. So what I'm trying to do here is I have some weight for each classifier. Now I'm trying to minimize this weighted error. Is that clear? Okay. Once you do that, we are going to evaluate a bunch of quantities. Okay, so the first quantity is epsilon m. Okay, we will talk about what these terms are. So summation n is equal to 1 to capital N, Wn of m, indicator function of ym of x of n, not equal to p of n, divided by summation n is equal to 1 to capital N, Wn of m. Okay. Now we're going to talk about what is epsilon m, but like intuitively, like what do you think is epsilon m? So look at the numerator and denominator.
Measure of correctness.
Sorry?
Measure of correctness.
So what do you mean by measure of correctness?
Correctness of the prediction. So whenever the prediction is correct, the weights would add up.
No, whenever the prediction is not correct.
Yeah, not correct, the weights would add up. So if the value is high, then the accuracy is low.
Yeah, so in some sense, this epsilon, okay, if you look at the denominator, it's sum of all the weights, right? However, the numerator is just a sum of weights for incorrect examples. So in some sense, this is like an error rate, but weighted error rate, okay? And we will also compute alpha m, which is the weight that I mentioned. So ln, it's basically ln 1 minus epsilon by epsilon. Okay. Then as a last step, I'm going to update the data weighting coefficient. Okay, so Wn of m plus 1 is given by Wn of m, which was initially 1 over m, multiplied by x of alpha m, indicator function of ym of x of n not equal to t of n. Is that clear? Now, so what does this mean? So this means that after training, okay, I'm going to increase the weights for classifiers. So how am I doing that? So I'm doing that only if the indicator function is true. So if this is 0, that means there is no incorrect prediction for that example, right? So then this whole thing becomes 0. So I'm not changing the weight. However, whenever the prediction of this model is wrong, which means it's a wrong example, like classifier makes mistake for this example. So I have to increase the weight. So how much I'm increasing the weight? I'm increasing it by x of alpha n. Is that clear? Okay. So now you can continue this process m times. Okay. So just to repeat, we started with giving 1 over n weight to all the examples. Okay. Now in every iteration, we fit a classifier by using the weighted error function. Once you have the classifier trained, then you evaluate these quantities and then you update the weight. Okay. Now you repeat this process for n times. So once you finish that, finally, we are going to combine this thing together to come up with our final model. Our final model ym of x is given by sine of summation over m is equal to 1 to capital M alpha m ym of x. Is that clear? Okay. Yeah.
What m is the number of times you want to do it?
Capital M, maybe? So that's the number of classifiers we have. So n is the number of data points. Okay. M is the number of classifiers. Is that clear? Okay, so far it's good, but I haven't really told you like where did that alpha m and epsilon m come from, right? Like that is what we are going to see today. But for now, we have an algorithm which works in a sequential fashion by reweighting mistakes of the previous classifier, right? Now, before we try to understand how we arrived at this algorithm, let us look at an example. Okay. Now, here is an example of how boosting would work. Okay. In this case, I'm going to use very simple classifier as my base classifier. Okay. So the base classifier is basically the type of classifier that you're using for boosting. Okay. So the base classifier I'm going to use is what is known as decision stump. Okay. So this is an extreme form of decision tree. So if you think about decision trees, like you take a feature, you make some test, then you go to the next level, you make some test, go to the next level, make some test, right? Like so, it's a deep tree. However, decision stump is a tree with just one node. Okay, so you randomly pick a feature, and you make a test based on the feature. Like so, for example, in this case, like you have two features. Okay, so in this case, you have theta 1 and theta 2, two features in the data in this task. Okay, so you can have one decision stump which basically checks if theta 1 is greater than 0. Okay, maybe let's do a real example here, right? Like so this is theta 1, theta 2. Now, if you think about this particular line that you see, the green line, okay, that is a decision stump which is theta 1 greater than 0.5. Okay, now that is my classifier. This classifier will check if theta 1 is greater than 0.5, which means it will come to the right side as one class, and anything which is less than 0.5, theta 1 is in the left side. Is that clear? Now it's a simple linear classifier, right? Like it can only draw a line. It is even more simpler than the linear classifiers you have seen so far, because this draws a line only like aligned with one of the features, right? Like so, for example, like you cannot draw a line like this because this requires a linear combination of both theta 1 and theta 2. The decision stumps can draw only straight lines or vertical lines, like sorry, horizontal or vertical lines. Is that clear? However, we will see in this example how we can construct really complex decision boundaries by just drawing horizontal and vertical lines. Okay, so let's look at this example. So here you have a bunch of red and blue examples, right? The goal is to come up with a classifier which will separate blues and reds. Okay, so initially we are going to give equal weight to all the examples. Okay, now the size of these examples that you see here is their weight as well. It's the relative weight. Okay, so initially for this particular case, you see that all the examples have same size, right? So it's 1 over n. Okay, now I draw my first decision stump, okay, which is basically this black line. Okay, so the green line is the combination of all the classifiers. It's the output of the boosting. Okay, initially there's only one model, so the green line is equal to the black line. Now you see that there are some mistakes, right? Like so, for example, you can see that this particular thing that I have highlighted is a red example. It is supposed to be in the right side, but it is in the left side. Similarly, this particular thing, right? And this particular thing, right? Do you guys see my highlighting? Okay, and similarly, in the right side, you have this blue and this blue. So these are the 5 data points where this classifier makes mistake, right? Now, you can see that when m is equal to 2, all these 5 data points are magnified, which means their weights are increased. We did not touch the weights of others, right? Like so, however, when you compare them relatively, you can see that others have smaller weight and this one has larger weight, right? So now I'm going to train a new classifier, okay, which is trained based on the weighted error function where the weight is given by this, okay. Now this new classifier is what you see here. Okay, so that black line. Now when you combine these two classifiers together, you get this complex, already nonlinear decision boundary. Is that clear? Then I can do m is equal to 3, another classifier. This is the third classifier that I'm learning. So when I combine these three classifiers together, I get something like this. Okay, and you continue like this, like you get this really complex decision surface. Is that clear? Any, yeah?
Is there a risk of overfitting?
Okay, that's a good question. So if you do boosting too much, like you will start overfitting to things in the training set. But one thing to remember is we would normally not do boosting with really good models. Okay, now we have weak learners, right? Like so these models are, for example, like just a decision sum cannot overfit. But of course, if you combine many decision sums, then you're going to overfit. So the overfitting problem is there, but there is also another serious problem here, like so, which is if you have mislabels, okay, a lot of other algorithms will graciously ignore that. Okay, however, decisions like boosting can be like very much affected by mislabels. Okay, so for example, let us say that there is one small blue here, but it is by mistake. Okay, however, boosting is going to magnify this mistake in every time step. That circle will get bigger and bigger and bigger. So you have a new decision boundary there. But in reality, person who was labeling these data sets probably mistakenly labeled a green, like a red as blue. Okay, so now that is another issue that you would have with this boosting problem. Okay, any other question? There are a couple of questions in the chat. Does the weight at each time step sum to 1? That is a good question. I'm not sure. I don't think so, but I can verify. No, I don't think it sums up to 1. Like it sums up to 1 in the first iteration, probably not in the future iterations. That's why we have the denominator, which is the sum of the weight. Otherwise, the denominator will be 1, right? Okay, so any question? Is the idea clear? Like so, like we have seen the algorithm and we have seen how it works. Okay, so now what is left out is the most important or crux of the algorithm, which is like, how do I find these alphas, epsilons, and like other parameters of this model, right? Like so, like what is my training? Like, well, we have seen the training algorithm, but like, how did we arrive at the training algorithm? Okay, now to understand like why boosting algorithm is like this. Okay, so we're going to talk about. I'm going to introduce a new type of error function. Okay, so which is the idea of exponential error function. Okay, so what are the different error functions we have seen so far? Another reminder. Yeah. Least squares. Okay. There are a lot of answers in the chat. Okay, least squares. Then yeah. Logistic regression loss. Yeah. Good. Anything else? Yeah. Hinge loss, which we use in SVMs. Anything else? Yeah. Yeah. The most important 0, 1 error, right? Like, which is what, like, we also discussed how all these other errors like least squares or logistic regression or error or like Finch loss is trying to do a continuous approximation of the 0 and loss, right? So now we are going to see yet another error function, okay, so which is what the whole idea of boosting is based on. So this is exponential error function, okay. Now the exponential error function is defined like this. So E is given by summation n is equal to 1 to n. As you can easily guess, this is going to be exponential of the mistake, okay. So it's going to be exp of minus t of n fm of xn. Okay, is that clear? Where this fm of xn, right? So that is my boosting classifier. Okay, so fm of x is given by 1/2 summation L is equal to 1 to capital M alpha L y L of x. And we also know that T of n belongs to minus 1. Is that clear? Now, so what is this exponential error function doing, right? Like, so now, whenever your model makes the right prediction, okay, so your error is going to be what? Your model is making a right prediction, which means T of n, we have seen this in perceptron. So T of n multiplied by fm of x of n is going to be positive, right? So because if this is +1 and your model is also making a +1 prediction, then it is positive. Similarly, if this is -1 is your target and your model is also making a negative prediction, then it is also positive, right? So whenever the model is making the right prediction, it is going to be e power minus something. Whenever the model is making wrong prediction, it is going to be e power positive value. Is that clear? Now the goal is to minimize this error function. Is that clear? Okay. Now, however, this is not an easy error function to minimize because of this combination of many classifiers. Okay, so there are two things that we have to learn. So we have to learn the classifier, the base classifier parameters, and we also need to learn these alpha parameters. Is that clear? Our goal is to minimize this exponential error function with respect to both the weighting coefficient alpha L and also the parameters of the base classifier YL of x. Is that clear? Now, typically when you do gradient descent, what would we do? We will compute the final loss. We will differentiate with respect to alpha L, all the alpha L's. Similarly, we will differentiate with respect to all the YL's parameters, right? And update the parameters by using a gradient descent update rule, right? Now, instead of doing this global minimization, okay, so what boosting is trying to do is a sequential minimization. Or in other words, we will first learn the parameters and weights for the m-1 classifiers, and then learn the parameter and weight of the m classifier. Is that clear? So we are doing this sequentially. So what we are doing is we are going to learn y1 of x to ym-1 of x. Okay. Also, we are going to learn alpha 1 to alpha m-1. After fixing these things, okay, we learn these things, we'll fix this, and then, okay, so you fix this and then learn alpha m and ym of x. Is that clear? Now you do this sequentially. So initially nothing is learned, so you will just learn alpha 1 and y1 of x. Then fixing alpha 1 and y1 of x, you're going to learn alpha 2 and y2 of x. Then fixing alpha 1, alpha 2, y1, y2, you're going to learn alpha 3 and y3 of x. And you continue. Okay. Now this just becomes easier now because we just need to compute gradient with respect to 1 alpha and 1 y, and then like we know how to do this easily, like differentiate set it to 0, right? So like then you have the value. So then you move to the next classifier. Is that clear? Now to do this, like we should also decompose our error function. So my error function E, which was summation n is equal to 1 to capital N, okay, x of, where's error function? I think I need a half in the error function, but it is okay. Okay, so x of minus t of n, f m of x of n. Right? So this was my error function, but this includes, okay, there is something wrong in the way I have written this. Oh no, this is fine. Okay, now, so this is my exponential error function when you have m classifiers, right? Now this contains m minus 1 classifier and the final classifiers. I can actually decompose this error function. So the way in which I'm going to decompose this is summation over n is equal to 1 to capital N, x of minus t of n, f m minus 1 of x of n. Okay, so this is a boosted classifier with just m minus 1 classifiers. Okay, minus 1 over 2 t of n alpha m y m of x of n. Is that clear? So what have I done here? So I have added the final classifier, like the like the mth classifier. Okay, so if you look at the actual equation, the mth classifier was added by multiplying by alpha L by 2, right? So I'm multiplying by alpha m by 2 and I'm adding the mth classifier. Is that clear? So now what I have done here is I took the original loss, okay, where fm was supposed to be summation over all the m classifiers, right? And I separated it into two parts. There is one part of the loss which is based on m minus 1 classifier, and there's another part which is based on just the m classifier. Okay. Now, when we differentiate with respect to the parameters, this is constant, right? So this is based on the previous classifiers. So I can safely ignore this and just focus on minimizing this with respect to this part, right? So, like I'm just going to make this the first part to be a constant. Okay, so summation n is equal to 1 to capital N. Okay, Wn of m, x of minus 1 over 2 t of n alpha m y m of x n. Okay, where the Wn of m that you are seeing, okay, is nothing but x of minus t of n f m minus 1 of x of n. Okay, so just this part, since it is a constant, I'm going to give it a name, let's say w. Okay, and you have the rest. Is that clear? Any questions? Okay, so there is a question in the chat. Why do we use 1 over 2 here when I splitted the things, right? So it's because you see what is fm. So fm is basically 1 over 2 summation over n is equal to 1 to m alpha l y m. If the question was why do I have 1 over 2 here, you will see that later, because when you differentiate, it's going to help us cancel things. Okay, so it doesn't really matter. And that is what is here. Okay, there is another question. So do we have something that states that the overall best classifier is a combination of the best, weak, classifier? Okay, that's a deep question. So the question is there any guarantee that like this is an optimal thing to do, like training sequentially? I think there is a lot of theory on boosting, but I don't remember anything off the head. So probably I will put some references. Okay, so now is this clear? Okay, so now you look at this particular equation. Let's take this to the next page. This is my new error function. Okay, so this is my new error function. Okay, now this Wn of m is a constant. We don't need to worry about that. So all we need to do is somehow minimize this error function to find the best alpha m and ym of x. Right? Now, to do that, we are going to first separate our data set into two parts. The examples where my ym of x makes some mistakes and examples where it is not making mistakes. Okay, so the first set is, let's just call it as tau m. Tau m is basically set of data points, okay, that are correctly classified by ym of x. Okay, similarly, let's have mu m, which is basically the set of data points which are misclassified by ym of x. Okay, so if I split things into that way, then I can actually write this error function like this. Okay, so now my error function e is going to be, now if it is correctly classified, then we know that p of n multiplied by y of m is 1 plus 1, right? If it is wrongly classified, it is minus 1. We are going to use that idea here. This becomes e power minus alpha m by 2 times summation over n belonging to tau m yn of m plus e power. So when it is wrongly classified, this multiplication is going to be minus. So minus multiplied by the existing minus, it becomes plus. So e power plus alpha m by 2 summation over n belonging to mu m wn of m. Is that clear? Now, probably this is the most non-trivial step. I want to make sure that you understand this. So I took my error function. Okay. Now this error function is summation over n is equal to 1 to capital N. Right? It is over all the examples. Now I'm going to divide the examples into two sets. One where my model is making mistakes, one where my model is not making mistakes. Okay. Wherever the model is not making mistakes, that set is called tau. And wherever the model is making mistakes, that set is called mu. Okay. Now I'm going to split that summation over n is equal to 1 to n into two summations. Okay. So first summation is over correct examples. For correct examples, we are going to get wn e power minus 1 by 2 alpha m. Right? Because for correct examples, t multiplied by y is plus 1. I mean, like examples where model is correct, right? So now that is what this term is. So this e power minus alpha m by 2 is not a function of n, so I took it out. Okay. Similarly, for incorrect examples, it is going to be summation over incorrect examples wn multiplied by e power minus 1 by 2 alpha m multiplied by another minus 1. So this becomes e power alpha m by 2. Summation over the incorrect examples. Is that clear? Okay. Now I'm going to take this. So I'll just finish this in a minute and then we'll do a break. So I'm going to take this. Okay. Now, I'm just going to do a little bit of algebra here. So which is the the error function is going to be e power minus, okay, so I'm going to add and subtract something, okay. Now, there is e power alpha m by 2, okay. I'm going to put minus e power minus alpha m by 2, summation over n is equal to 1 to capital N W n of m, indicator function ym of xn not equal to p of n, plus e power minus alpha m by 2, summation n is equal to 1 to capital N W n of m. Okay, so what did I do here? Okay, so I just added and subtracted something. Okay, so let's look at what I have added and subtracted. Now, if you look at the first term, so the first term is just a summation over correct examples, right? Now, instead of that, I am putting summation over all the examples, right? Which means I have added e power minus alpha m by 2 for incorrect examples. I'm just subtracting this here. So I'm subtracting e power minus alpha m by 2 for all the incorrect examples. So that together, there is nothing changed. But this is just going to be convenient for us to deal with. Is that clear? So now, our goal is to minimize with respect to alphas and y, right? So the goal is to minimize with respect to alpha m and ym of x. Okay, we will just do minimization with respect to ym of x now. Then after the break, we will do with respect to alpha. So it's very simple. So once you have this error function, now you see that there is no ym of x here, right? So when you differentiate, this term is going to be 0, right? Similarly, you see that there is no ym of x here, so this is a constant, right? So the only place where you see ym of x is here. So you just want to minimize this particular thing, which is exactly what Adaboost is doing, right? So like Adaboost is trying to do exactly the same thing, which is basically minimizing summation over n is equal to 1 to capital N Wn of m, the indicator function of ym of xn not equal to t of n. Is that clear? So now there is a principal reason why that step in Adaboost is the right thing to do. Now, similarly, we are going to talk about how to differentiate this and minimize this with respect to alpha m, so which is going to give us the formula for alpha m and epsilon m. So then we are done. Okay, so we will take a break here and continue at 1:50.